Okay, so I've uploaded quite a bit more information on exchange as well, to try and sort of bring some of the concepts alive. And the thing you've got to remember with alloys, I think we'll start with the idea that we're building a plane and we're using alloys, okay? So we'll start with that scenario, okay? Building an aircraft, okay? Using aluminium alloys. Now, of course, you use other things as well, but just for this section, we'll just think about being aluminium, okay? And the first thing you've got to remember with an alloy is, well, first you've got to know what an alloy is, okay? So what's an alloy? Good. Combination of two metals.
Two or more.
Yeah, two or more. Now, it sometimes has other things that are non-metallic, like silicon in as well. Like in those notes, I talk about silicon assisting in casting, lowering the temperature. But combination of two or more metals. So we already know, I think of it as like being a hybrid metal. Okay? So when we're building this aircraft, we melt the two metals, okay, and we put them into an ingot. And so if we're talking about our alloys, first thing you might want to think about is trying to remember some of the different numbers, okay? Now, trying to remember them all, I don't think is necessary, but if you try to remember, for instance, that 1 is aluminium in the code, like 1 and the 3 numbers after it will be an aluminium, okay, pure aluminium. 3 is manganese, 5 is magnesium. Okay, if you try to remember those things, that might help, okay? So we know that the, 1xxx is aluminium and 3xxx. I can't remember the chemical symbol for manganese. And 5xxx is magnesium. Is it Mn?
Mn.
Yeah. So that's something that's worth remembering. And then like 2xxx is the copper alloys, okay? And 7 series is zinc, okay? If you remember that and some of the characteristics of those things, that's going to be helpful, okay? So that's something that you might want to think about when you're making your notes, that you remember some of those alloys. Okay, something else about those alloys that's that you'll need to get your head around is cold working and hot working. In other words, non-heat treatable versus heat treatable, which we have in the notes. So last night I was trying to get my head around a little bit around, because it's metallurgy and it's really complex, so it's not a simple thing, but this idea of cold working. I wanted to try and find a very simple explanation for it that you can put in your head that might make sense, and that you'll be able to communicate if you're asked a question about it. And what I found was, and I'll show it after I go through this, I'll show you it on Exchange. What I found was there's this Canadian woman that was talking about a bowl of ice cream. Okay, sorry for my very bad drawing. And she said if you put a spoon into your bowl of ice cream and you push really hard, the ice cream's frozen, the spoon will bend, okay? So that is plastic deformation, okay? So we know about that from previous work that we've done. So that is plastic deformation on a macro scale, on a large scale that everyone understands. Bending of the metal. if you look at a metal sort of microscopically, it forms this. And what do they call this? Do we know?
Crystal lattice.
Good. It's crystal lattice. So this is at a microscopic level. And when you apply a force to the lattice, it will bend. Okay. Now, if you don't exceed the limits, the elastic limits, it'll spring back. But if you apply enough force to this substance, you'll eventually deform it. Okay. Now, the explanation that you'll see in the video is really, I think it's a really good one. What they're actually saying is, more often than not, you do not have, anytime you have a metal, you do not have a perfect lattice. Okay, there is deformities in the lattice. So you might have a deformity where you've got a dot missing. Okay. And wherever you've got something missing, I don't know if you can actually connect them that way, but wherever you've got a dot missing, you've got a weakness, okay? And when you apply a force, what's going to happen is, and the video will explain this a lot better than I can, is that weakness is going to want to travel. So the thing you've got to take away from this is that the deformity in the lattice travels. Okay? So as you apply a force, this deformity is going to want to move across. Okay? It's on its way. Now, if it's just one deformity that's happening and travelling across, that's not telling you why the metal gets harder, is it? It's just something moving across. But what they're saying is that in this process of cold working, and cold working could be, we'll define what cold working is. Okay, cold working is bending, pulling to make wire, pressing, etc. So it's working the metal. So you can grab a copper pipe. You can actually try this if you ever get a piece of copper. I've got some at home. I might bring it in to show you. I'll bring a few pieces of it in. When you bend your copper pipe the first time, pretty easy. Then you try to bend it back, and it's like, all of a sudden it's changed. Material has magically become stiffer. That's cold working, okay? What happens is these deformities move across, and it's basically, if you've got a perfect lattice like this, it's able to slide across itself quite easily. There's no obstructions, okay? So it'll tend to shear across these boundaries here, and you've got this lovely smooth transition happening, so it's really easy to work. But when you've got these deformities, these little lumps all over the place that have travelled across from various places, it creates a traffic jam essentially, and it makes it very hard for the material to move. So once you start these things moving, okay, in all different directions, they get in each other's way. That's one of the theories. There's a few theories online that you'll find. But I think that's a really good one. You start with this idea of a macro deformation, and then we go to the micro, and we talk about deformities travelling, and if you've got enough of them in a small enough area, you get a harder material, okay? So you've just got to remember that that is the basics of cold working, and we will watch the video to get an idea of it. So cold working, some alloys are cold workable, and I'm pretty sure, from memory, but you might want to check this, that they cold work, okay? So if you want a cold worker material, aluminium, the 3 alloys, the 5 alloys with magnesium, you can do that, okay? To a point. Obviously, if you keep cold working, it gets harder and harder, and eventually it gets brittle and it breaks, Okay, so there's benefits and disadvantages, and it's a balancing act between being hard but not being brittle. And you'll find that all these alloys are tweaked up with different percentages of different trace metals to try and get the perfect material for the position that it's being used in. Are we all okay with that concept? And it will become a lot clearer with the video as well. So that is cold working. And then you've got hot working. Or heat treatable, or heat treating they call it. And we looked at, I want to make sure I get my terminology correct too. Solution treatment, I think it's called. So this is sometimes called strain strengthening as well. Heat treating, solution treatment. I found a really good video that explains this really, really well. So we'll watch that in a second. Solution treatment is heating. You don't go up to a melting point, but you take your alloy that you had to melt to create the alloy. So you've created this ingot that you're going to use to create your aircraft. Now, any of the materials that are this type of alloy, you're going to do cold working on to get them to the strength that's required. You'll roll them into sheets. You'll do whatever you need to do to get them to the strength that you require. When you come over here to your heat treating types of alloys, you're looking at your copper and your zinc. Okay, this zinc one's extremely strong. It's used for the superstructure of the aircraft. And you're going to use solution treatment and then aging processes. Okay, so solution treatment is heating, so not to melting. Because this is something that I got a bit confused about when I'm talking about precipitation, because if you've done chemistry, precipitation is something completely different to what this is about. Okay, so if you're kind of trying to apply that knowledge, you get a bit confused. Even the idea of quenching and soaking. I thought soaking was like sticking it into a solution. Is there a question?
Yeah, I was just wondering what the lattice is called.
Crystal lattice, sorry. And there's a much better explanation of this on the video, and we'll watch it, and you might want to take some notes from it. Solution treatment. You heat your metal, your alloy. Heating, and then soaking. Now, soaking isn't putting in a liquid. It's leaving in that heat for a period of time. You see that when you're firing ceramics too, they call it a soak, where you've actually just left it at a particular temperature for a particular period of time. So leaving in heat for a period of time, and then quenching. That is cooling. Usually in a liquid. So solution treatment is heating, soaking, and quenching an alloy to leave it in a softened state. Okay, so that's the start of the process. That's solution treatment. Okay, so with the cold working, we start with an alloy that's already soft, and we cold work it until we get it to a particular strength that we require. Here we have heat treating, and we start the process with solution treatment, which is heating, soaking, and then cooling or quenching. And at that point in time, and you'll see in this video, it's quite interesting, the metal is actually soft if it's an aluminium alloy. Now, they started using this process because with steel, when you want to strengthen steel, you use exactly the same process. Obviously, steel is iron and carbon, okay, an alloy of iron and carbon. And depending on the amount of carbon, you've got different strengths of steel. But then you can actually heat it and quench it in water. And you'll see that ever seen your blacksmiths doing this, where they heat it to red hot and then they to cool it down? That makes it stronger, okay? So the person that first tried to make alloys of aluminium, because when they first started the history of aviation, someone thought, well, aluminium is a great material, it's so much lighter than steel, but it's really soft. It's not really good for building aeroplanes. So they thought, well, I'll just do this to it, what you do with steel. And very disappointingly, it was still soft. Okay, and we'll see in the video what happens later on. In fact, we might watch it in a second because it might help things along. But it's soft initially, and then something really magic happens over time. Okay, and that's where we talk about age treatment. And you've got, and I just want to make sure I use the same terminology as you've got in your notes, because otherwise we're going to get very confused. Natural aging. So, then we've got natural aging. And that's not like letting yourself go. It's taking this solution-treated alloy, okay, and it's leaving it for 6 to 24 hours at room temperature. So when you first take it out of that solution treatment, you go, bend it over your knee, and you go, that's no good, it's useless. But if you come back in 6 to 24 hours, grab the same piece of aluminium alloy, okay, that's one of these alloys here that's heat treatable, and try and bend it, can't bend it. Suddenly, overnight, it's changed. It's become stronger. Okay, so that is natural aging. You take your solution-treated alloy and you allow time to let the magic happen. We've got a video of how that happens, okay? You've actually, and I'll explain why it's stronger as well when we do that. So natural aging is allowing your solution-treated alloy, and I think they said 6 to 24 hours. To harden, okay? At room temp. Now you will have situations where they will take this solution-treated metal like a rivet, or where they don't want it to be hard when they're using it. They want it to go into whatever they're putting it into and then become hard once it's in place. So you'll actually find that they quite often will take something that's solution-treated and take it to below zero, freeze it, and then when they want to use it, take it out, put it wherever it needs to go, and then allow it to naturally age in situ. Okay, so there's talk in your notes there about using refrigeration to slow that process down, but that's something that they do. So that's something to keep in mind too. But natural aging happens room temperature, 6 to 24 hours, and it hardens the metal, okay, and brings it up to whatever strength you require. Now the aging process, obviously, after a certain period of time will stop. It's not going to just keep getting harder and harder and harder until the plane's like a piece of glass. But you will notice over that first 24 hours or so that's when it becomes its strongest. Are we all okay with that concept? If we're not, we will be when we watch the video, hopefully. So that's natural aging. And then you've got artificial aging. And that's where you use heat to speed up the process. And in your notes, under artificial So instead of you leaving it at room temperature, it's soaked in an oven. I might have got those times around the wrong way. Sorry, tell a lie. It's 16 to 24 hours. And this is soaking in an oven. Use heat to speed up the process by soaking the part in an oven, and I think it's at 100 or 200 degrees, so it's not incredibly high amounts of heat. Yeah, 100 to 200 degrees Celsius. Degrees C for 4 to 24 hours, okay? This is sometimes known as precipitation. Hardening. Okay, so these alloys here, the 2s and the 7, okay, are the ones that are heat treatable. Okay, this one here, like I said, coal working, which is non-heat treatable. So that's how you treat your, yes?
So would there be a difference in the result between natural aging and artificial aging?
That's a really good question. I'm sure that there's differences in how they behave. I'm pretty sure that the precipitation heating happens with these. I'm sure it happens with this one here, the 7 series, which is really strong. So I would say that for the really strong ones, they're actually using the oven process. Don't quote me on that. Okay, but there is a difference, and that's why there'd have to be a difference, because it wouldn't be for the sake of waiting, because you're heating in the oven for the same period of time as a natural aging process, so there must be an advantage to it. Okay, obviously some things will age naturally and come to the required strength, and they've obviously discovered with certain alloys that you can't do that. Okay, but there is a difference, obviously. So you've now got a few words you can use. You've got a solution treatment, and you've got precipitation hardening, okay, which is where you artificially age rather than natural age. So there's a lot of terminology there, okay, but if you imagine yourself building your plane, remembering that some are hot workable and some are cold workable, in other words, non-heat treatable or heat treatable, and you remember your bowl of ice cream, and soon when we watch these videos, I'm hoping that that'll make things a lot clearer as well. Have we all got that down? Because I'm going to rub it out, and we'll play the videos, because I think the videos are going to help a heap. Because yeah, it's a lot of information, and you've got to. It's a bit of a trade-off. Obviously, if you're really good at remembering numbers and codes and everything else, if you can remember the 4-digit code, in your notes there, they actually tell you that each of the alloys has a code. Okay, and you can read the code, and you can say if it's heat treatable or not heat treatable, whether it's aged naturally or aged unnaturally, how hard it's been aged to, like the actual time it's spent in the oven. All that sort of stuff can be read from looking at the code, and that's in your notes as well. So that is worth looking at. I don't think you need to memorise the entire code. You're not becoming metallurgists, but understanding that there's these different processes, and the basic concepts behind the processes, I think, will be a beneficial thing. I have seen some questions where they've asked about that idea of precipitation hardening. Okay.